So, ladies and gentlemen, good morning. We are in the course of quantum transport. A week ago, we've been talking about interaction, about Coulomb blockade, departing from scattering theory. Now I would like to get back and again talk about the scattering, but I will bring a new topic. I will talk about superconductivity. Superconductivity is rich subject. Those who who are taken to advanced quantum mechanics course know a lot about this. We don't need much of the superconductors. We look at basic properties, and we will understand what we will need from the superconductors in the context of scattering. We will talk about Andreev reflection, spectacular phenomena. We will look at the nanostructure, which is placed between normal metal and superconductor. And actually, we'll discover that the scattering approach we know is very much suitable, is very much sufficient to describe this situation. Then we turn to the nanostructure between two superconductors, and that will bring us to Josephson effect. Josephson effect, persistent current, oscillating current. We'll talk about all this. We'll understand how to relate Josephson effect to bound states. That will be again an exercise in scattering. We will talk a little bit on classical dynamics of Josephson junction. What is that? Because in a week, I would like to combine Coulomb blockade and superconductivity that will bring us to wonderful world of homemade quantum mechanics, one of the big achievements of quantum transport. Very good. Sir, as usual, please put your question to the chat. I will be ready to answer this. If question is not answered, please speak up. So quantum transport in superconducting devices. Let me talk first about basic properties of superconductors. And those who attended advanced quantum mechanics course have been recently exposed to the story of discovery of superconductivity in Leiden, not in Delft, by Professor Camerlinonis. That was more than a century ago, and it was totally unexpected by the time. And one could hardly imagine that it is expected by anybody. It is a spectacular discovery, essentially experimental, that resistance of many metals quenches at some critical temperature, and the material becomes totally superconducting, given no resistance to electric current, which means that electric currents can go spontaneously without and persistently without applying any voltages. That's what people later have seen as Meissner effects. if you take a superconductor, you put it into a magnetic field, the field cannot go to superconductor. It is expelled, it goes around. That means that there are currents, in the direction perpendicular to this light. That would be minus, that would be plus. Currents in this direction around the superconductor that actually repel this magnetic field, cancel it inside the superconductor. So it is a property of superconductor, persistent current, and it causes very little energy to produce these currents. And people have wondered why this property. It took quite a long time to discover the mechanism of superconductivity and finally understand what is going on. The mechanism, as a short cartoon, is as follows. Electrons in superconductor, they form pairs. They kind of come together and they come with opposite spin and momentum. So there are Cooper pairs at zero momentum. And since there are bosons, being combinations of two electrons, they condense. And the superconductor can be seen as a condensate of this Cooper pairs. It means that it's very easy to put the double charge to create a Cooper pair in superconductor or extract Cooper pair. You don't even change the state of superconductor. So it applies that in superconductor with respect to charge additions is in a macroscopic quantum state. To characterize the state, one could use order parameter. The modulus of this order parameter kind of shows how strong is superconductivity. This is natural, but it is to characterize anything by a number, right? Strong or weak, strong, a bigger number. But what is essential that this order parameter is a complex number. So there is a modulus of this parameter and the phase associated with this. It happens so that if you make gauge transformation, you also change this phase. So the superconductors provide an example of spontaneously broken gauge invariance. This is closely related to the fact that you don't have to pay any energy in order to extract charge or add charge to superconductor. Sure, in advanced quantum mechanics, we talk more about this. So now let us just take it as a fact. All fancy properties of superconductors are explained by the fact that superconductors are characterized by complex order parameter. They have phase. And these currents are eventually gradients of this phase. Fine. What else? How shall we proceed? I will add more detail. I will talk about a spectrum of charged excitations in a superconductor. First of all, let us forget about the superconductivity. Let us understand, perhaps it's not first time in your life, let us understand the charged excitations in a metal. right. So here I made a small plot. What I plot here is an electron energy in a metal. I counted from Fermi energy, but perhaps to make a small plot. There's some spectrum in the metal, energy versus K. Some states are filled. Some states above Fermi energy are empty. And what I take for energy is just this distance, which can be positive, which can be negative. Now, I would like to understand what are excitations. Well, I could put an electron over here, and that's the spectrum. Just has energy which is zero at Fermi level and increases if you go further. I could extract an electron making a hole in superconductor. Okay, this is a hole. Right, and that also causes positive energy because I have extracted an electron with negative energy. Sure, that gives us a spectrum. It consists of two branches, electron branch and hole branch. And as you see, near Fermi energy, it costs no energy to create this excitation. That's why metals are metals. That's why they conduct. What happens if they superconduct? Let's recall the fact that we can that we have condensate and that we can add or extract particles to prepare from this condensate. Right. Let us think of Hall excitation. It could absorb a Cooper pair from condensate and become an electron. Similarly, an electron can dump charge to E to condensate and become a hole. So in the presence of condensate, electrons and holes are not really independent entities. They can transit from one to each other. Moreover, this transition is not associated with any energy dissipation, with any change of the state. It is a coherent transition. That's why the spectrum of a superconductor is deformed like this. Instead of this cusp, we have a smooth hyperbola. And there is a gap opening at Fermi energy in the spectrum. This is the spectrum, and what about kind of eigen functions of the spectrum? What about discharge excitations? They become coherent superpositions of electron and hole. So let's call it quasi-particles. And wave function of a quasi-particle is a superposition of electron and hole state with some coefficients, alpha and beta. Right. These coefficients do depend on the spectrum. Here at Fermi energy, we have just equal weight superpositions. So moduli of alpha and beta are the same. Well, here, apparently, you see as the spectrum becomes closer to holes. That's why we have, that's why the quasi-particles are mostly holes. Here, they're mostly electrons. Good. So it is important for us at the moment that there's energy gap in the spectrum. So in fact, the spectrum of superconductors is very similar for, at least in shape, to that of semiconductors. So there's a gap, you know, for in semiconductors for charge excitations. That's why at zero temperature, semiconductors are insulators. There are no charged carriers. There are no charged excitations. So my question, let us call it quantum question, why superconductors are not insulators? Why they conduct electric current? So the spectrum, it is the same spectrum as in semiconductors. The quasi-particles would not be present at low temperature. But okay, this is a correct answer. Cooper pairs by themselves can provide current. Unusual current, a flow of condensate, that's why it does not meet any resistance. A quasi-particle current would require some voltage to go. Right, sir, and it is okay. That implies that I will have to pay energy if I want to add a single charge to create a single excitation in superconductor. But it's perfectly fine to add two charges, pay no energy. Good. That looks rather abstract, and we will see just in a minute how does it work in the context of scattering. It works in very peculiar, but trust me, very simple way. That's where we start our discussions. For simplicity, let me start with a minimum of details. And what I want to understand how electrons from normal metal can eventually go to superconductor. First of all, I need to provide something to go with, right? So I would connect normal metal and superconductor with ideal nanostructure with quantum point contact, where we know for sure there are no reflection. So electron, once it enters the nanostructure, it cannot turn back. It has to go to superconductor. All right, no reflection in the nanostructure. Well, okay. And if it goes at energy which is smaller than this gap energy, we understand that it just cannot go to superconductor. There are no excitations at this energy. And it has to be reflected somehow, but it cannot. And this strange process is called, let's remember these words without understanding meaning yet, Andreev reflection. Fine. This process, Andreev reflection, also happens if the energy is higher than the gap energy. Because anyhow, electron which has definite charge should be converted to a quasi-particle which doesn't have a definite charge. That does not match, which means that part of the excitation must go away somehow. All right. So let us see what is this mysterious process. Good. In essence, what happens is the following. Electron which comes to superconductor gives the charge to the condensate. So it becomes a hole. Hole is the absence of electrons. So it just it means that its velocity has changed to opposite. And the initial electron is converted into hole and goes back to normal matter. All right, that looks a bit crazy suggestion. Let us make a quick foolproof. If this satisfies some basic principles, conservation laws. Let us check conservation laws. First of all, energy. Energy is conserved by this process. So we have electron at some energy, at some level, epsilon. The resulting hole will have the same energy. Fine. Charge, since electron is converted to hole, it looks like the charge has changed, but the total charge is conserved. Since a Cooper pair in condensate has been created. That is very strange. That reminds me this famous Dutch saying, which is still used in advertisements, I believe. We actually pay one charge, we send one electron, and we get 2 electrons transferred to superconductor. Right, that's how the charge is conceived. Momentum is also conserved despite, except perhaps very small quantities associated with smooth change of momentum along this ideal nanostructure. One has to take into account that again, hole is the absence of electrons, so it has the same momentum, but velocity is opposite. What about spin? Spin is also conserved if electron had spin up, the resulting hole will also have spin up. Fine. Andreev reflection. So it seemed to be the only logical possibility. So let us accept it first without any, microscopic details, without any complex formulas, which would help us to imagine the details of this process. But it was at the particle level. Let us try to understand what happens with the waves. All right, so let's recall that electrons and holes are waves. And electrons are, as we have seen, are converted into holes. What does this mean in terms of wave function? It means that the wave function in a superconductor has become a two-component wave function, right? It's the only way in quantum mechanics to incorporate the fact that one sort of particles can be transferred to another sort of particles without dissipation. Right, so in fact, wave functions of excitations in superconductors, they have two components, and they obey an extension of Schrödinger equation, which is called Bogolyubov-de Gennes equation. All right, let us. Yeah, I promised to not intrude too much with formulas, but let us quickly look at the structure of this equation. So it has electrons and holes, and the whole Hamiltonian of this equation consists of 4 blocks. Those are diagonal blocks, and the usual, it just for which describes kinetic energy, which describes scattering of electrons into electrons or holes into holes. It's just usual Hamiltonian, right? It's diagonal blocks. Holes are kind of inverted with respect to electrons. So one encounters the same Hamiltonian, but with minus sign, giving opposite energies. Fine. But there are also elements which are associated with superconductivity. And as we see, the off-diagonal elements, they eventually mix electrons and holes. Fine. This is an equation in superconductor and normal metal in the whole system. And right, it has some eigenvalues, superpositions of electrons and holes. Let us look a bit with, yeah, I forgot to say that eventually it's a magic mirror, which I promoted several lectures ago. All right. So let us recall that electrons coming to superconductor are reflected as holes, and the momentum is the same. So the velocity of the hole is exactly opposite, right? So here I have considered an electron which came from this point. Well, it can scatter at some impurities, whatever, so it's not ideal transmission. And finally, it gets to superconducting interface. And at this moment, it converts into hole, and it goes in opposite direction. Okay, it's a wave. Yeah. And as a wave, it follows precisely all these scatterings which have been experienced by electron which went to superconductor. The hole just traverses this path exactly and comes to the same point. So eventually it cancels the scattering in normal metal. Oh, could have practical applications. One could see through mist in this way. Right, scattering basically conceals the light. But now if a part of this light is reflected from superconductor, it comes back again, it comes back to again to the source, and the scattering is cancelled. Good. So Andreev reflection as magic mirror. and we go to waves instead of particles. All right, are you still here with me? Any questions, suggestions, comments? How can I help you to understand this particular process? I mentioned partial Andreev reflection. How does that work? Is a superposition created in the normal matter. No, Sasha, in a normal metal, there could be no superposition because electrons and holes in metals are definitely different entities. Superposition can only exist in a superconductor. So let me sketch it as follows. All right, so again, there's normal metal, a superconductor, this is energy, so there's an electron coming at certain energy. And this energy is higher than the gap. Then the following happens. At this energy, it can exist as quasi-particle, but it cannot entirely go to quasi-particle. Why is it sure? Because a quasi-particle has wave function, which is superposition of electron hole, which is different from electron. That means that a part of electron has to be reflected as a whole. Sure, when electron goes at energy higher than the gap, two processes, two outcomes can happen. It either transfers as quasi-particle or is reflected as a whole. We will talk about this. Before that, let me add something which is important distinction. The important distinction between particles and waves. Let's see, there's a question. What does a part of the electron mean? Is there a superposition between a hole in normal metal and a transferred quasi-particle in the superconductor? Perhaps I have not expressed me clearly enough. There is initial state, electron. It comes to superconductor. And there are two possible outcomes of this event. Either it is a quasi-particle flying in superconductor, or hole which gets back to normal metal. In most cases, we are talking about classical probabilities of the outcome, correlations, possible quantum correlations between quasi-particle and the whole are gone. Oh, just because, yeah, by locality principle, quasi-particle goes to one side and whole goes to another side. Does this answer your question, Sasha?
Yes, clear, thanks.
Fine. Fine. Then let me add something important about Andreev reflection, which we totally miss in the concept of particles, but we have to mention it when we talk about the waves. Let us consider what happens to the electron which gets to superconductor in a little bit more detail. that conversion doesn't happen instantly in superconductor. Why is it, sir? The conversion comes from superconductive potential, which has quite small energy, say 1 milli-electron volt. And the electron needs time to feel this energy, which can be estimated from Heisenberg relation. So it would be inverse of 1 milli-electron volt. So it will be like 10 to the minus 10 seconds. Right. And for this 10 to the minus 10 seconds, electron is a speedy guy. It penetrates superconductor for quite a lot. Finally, it understands, oh, I'm not in my place. I could not become a quasi-particle. So it is converted into whole and gets back. So eventually, if one sketches wave function corresponding to the scattering process, it has a long extent in superconductor, extent which is characterized by so-called correlation lengths. That depends strongly on superconductor. In very pure superconductors, it can be like 100 microns, really microscopic length. Fine. And what is important that since the process is not instant, but rather long, there is a phase difference between incoming electron and outgoing hole. Right, so amplitudes of incoming electron and outgoing hole are related by phase factor. This phase factor, naturally enough, picks up the phase of the condensate, of superconducting condensate in this particular superconductor. Yeah, remember, all superconductors have phase. But it will become important for us that it also picks up some energy dependent phase. This energy changes a lot when at energies of the order of delta of the order of the gap. As we will see when we talk about states, that guarantees that all bound states are there in the gap region. Okay, energy dependent phase, Andreev phase, which is accumulated in the course of Andreev reflection. All right, let me get to what Sasha wanted to know. Let me get to a combination of Andreev and normal reflection. So instead of going to details, I would like to understand I would like to understand this as a scattering process. Okay, let me also leave the assumption of ideal nanostructure. So now an electron, yeah, here it is, an electron can eventually be reflected as an electron. No, sorry, can eventually be reflected as an electron in normal way, normal reflection, and it can be also reflected as a whole Andreev reflection. Very good. So let's get to the business. Let's recall what we know about Landauer formula, about currents associated with such waves. So I pose two control questions before we go to the break. All right. First, what is the current? In a single channel owing to this process. So we send an electron wave. There are reflection amplitudes given like this, and we wonder what is the current. So if everything is reflected, the current is obviously zero. If only part is reflected, the current is, I'm talking about normal reflection now. The current is like this, so it's just transmission, we know that. So what do I have to add to this formula to account for Andreev reflection? Yeah. Answer is modulus of Andreev reflection amplitude. Yes, sir. Let me put it here. And let me explain why. Because this wave, a whole wave goes in opposite direction, but it bears also opposite charge. So minus times minus gives plus. So this is a formula for the current. Sure, one can simplify this current at low energy. One can simplify this expression. How? Well, because in this case, we know that no electron go to superconductor, which means that outcomes of both reflections amount to what? Low energies to 1. Yes, yes, yes. They amount to 1. So one can simplify this formula with this expression. Well, for instance, one can express it in Rn in terms of Rr. And get the current in terms of Andreev reflection only. Very good. Let's have a break. Let's see, 7-minute break till 9:40. Go on. So here we are. We have understood the how to compute currents if you know Andreev reflection amplitudes and normal amplitudes. Let me just let me go very practical. Let me compute the resistance or conductance, whatever you say, of the nanostructure, which is placed between normal metal and superconductor. It's not obvious where normal metal is from this side. So there is normal terminal, and here it's a superconductor. And nanostructure is placed beside. Well, we need to assume something, but the assumption is rather relaxed. We just assume that reflection and transmission amplitudes do not depend on, so nanostructure do not depend on energy. do not depend on energy, which means that the structure is rather short. Or in more detail, the time to traverse the nanostructure is shorter than the time to make Andreev reflection, you know, to remember what I explained, get to superconductor and back, converting into hole. Very good. So let us see what we can do. Let us first define scattering matrix. Let's take one channel. We can sum up our channels in the end of the calculation. That's the scattering matrix for electrons. So there's some reflection amplitudes and transmission amplitude, which is the same, owing to from the left and to the right, and from the right to the left, owing to time reversibility. Okay, it is important for us that for holes, we will have the same scattering matrix, but all amplitudes will be conjugated. Why is it so? Again, because hole is kind of inverted electron. So if electron has wave function psi, whole wave function would go like psi conjugated, and all relations between wave function amplitudes will be replaced by conjugated quantities. Good. So the same nanostructure for holes will be described by complex conjugated matrix. Fine. So we know how scattering occurs over here for electrons and holes. Let us also recall that when electron is converted to a hole, that's what I showed here, it acquires a phase factor. Here I have it. So plus minus is here correspond to opposite conversion processes. As you see here, an electron can be converted to the hole, or hole can be converted to the electron. And the phase additions of the phase owing to superconductor are opposite. So if you remember our discussions about phase shifts, dynamical phases and geometric phases, that this part is dynamical phase. It doesn't depend on the direction of the process, while this is in fact geometric. It works like magnetic field. It changes sign upon time reversion. Good. So now we can combine all that and eventually get the amplitude of Andreev reflection. Yeah, so what do I have to do? It is very similar like we did for double junctions. But now kind of second junction is the same scatterer. Inverted because of Andreev reflection. It's too complex. Let us get to the numbers. Let me let me consider this process first. What is the amplitude of this process? Okay, we transfer the nanostructure, we get transmission amplitude. We acquire a phase factor at this boundary, and then in order to get the normal metal, we have to transfer this nanostructure as a whole. So it will be deconjugated amplitude, as I promised. All right, that's one trajectory, one possible process. There are more complex processes. What's the catch? The holes can be reflected from the back side of the structure. Okay, they are reflected here. They are converted to electron. This electron goes back, and it can be also reflected from the back side of the structure, and finally to be converted to the hole. All right. So we look at the contributions to Andreev reflection amplitude. Similarly, we could think of normal reflection amplitude. There will be different processes responsible for that, but let us concentrate on Andreev reflection amplitude. Good. So again, we have, as in the story about double junction, we have to add all these contributions to amplitude, and there is a factor associated with the bounce, and which gives us geometric series in this factor. Hey, here's the answer. Capital T's and capital R are transmission and reflection coefficients. You can see it from here. The product of these two is eventually transmission coefficient. Fine. So it contains this phase factors of Andreev scattering. Let us consider zero energies, and for zero energies, both factors are just minus pi, which are convenient. Minus pi over 2. Okay, this fake factor is irrelevant if we look at this. We have to square amplitude. We have to take model square of amplitude. So this first factor is not relevant. This becomes, okay, I have pi over 2, pi over 2. That is pi, exponent e pi, it's a minus 1. Okay, I have changed it to plus, and I square it. Here it is. We've got a chance of Andreev reflection, probability of Andreev reflection. As you see, it has resulted from lots of quantum interference between processes with different numbers of Andreev reflections. Fine. So it is a chance, and the chance cannot be bigger than 1. Of course, let us see what is important. At very small transmissions, this chance is much smaller than transmission of a single electron. Transmission of a single electron is proportional to transmission coefficient. This is transmission coefficient squared. But then it goes to 1 if transmission is ideal, right? So as we look at it, for Andreev, for ideal nanostructure, there's absolutely 100% chance that Andreev reflection has happened. So you can replace it by 1 and get 1. Fine, let's look at the current. Let us okay, we've made approximation of low energies, so we can see the voltages, which are smaller than the superconducting gap. And right now we can implement Landauer formula. So we have chances of Andreev reflections. And importantly, we have factor of 2. You remember where this factor of 2 came from. 2 Halle in 2 Halle 1 betalen. To get 2 pay in 1, we have sent 1 electron. We got two charges transferred. Fine. We could look at limiting cases. And as I said, if transmission coefficients are small, then Andreev, conductance of nanostructure between normal metal and superconductor is much smaller than normal conductance, because T squared is much smaller than T, if T is small. Very good. How about opposite limit, quantum point contact? Again, it shouldn't come as a news for you. In this case, the Andreev conductance is just doubled because of, again, of this factor of 2, a double charge transferred per a single electron event. Good, so it is less conductance at low transmissions. It's more conductance at high transmissions. If there is some transmission distribution, it could be anything, plus or minus, increase or decrease. It happens so that for most fundamental transmission distribution, which corresponds to diffusion, these effects of enhancement and suppression compensate each other exactly. And for a diffusive conductor, Andreev reflection is just the same as normal. Andreev conductance is just the same as normal conductance. Fine. So we cracked the problem. We have solved the problem, and we didn't have to know almost anything about superconductor except this Andreev phase. Right, everything is defined by scattering properties of the nanostructure itself. Good. Now I will change the setup. I will switch the topic. I will talk about Josephson effect, perhaps the most remarkable discovery of the end of the second half of 20th century. Good, that was like 50 years ago. Right, Josephson is a name. Professor Josephson is still with us. And by the time of its discovery, he was, was he a PhD student? Yes, he was a PhD student by the time. PhD students in England, they still are very young. It's perhaps of your age. Right, and was just, you know, a young guy with a fresh look, and he dared to understand what his colleagues had difficulties with. So what does he give to us? What has brought him Nobel Prize is the following. Let us take two superconductors, and let us connect it somehow with a weak link with a nanostructure or something. Then these superconductors can have different phase differences. And one aspect of Josephson effect, which is called DC Josephson effect, is that there can be a supercurrent through this contact, persisting current, which will depend on the phase difference between superconductors. So if the phases are the same, there is no current. If the phases are different, There's a current. It looks like if the voltages are the same, no current, there's a voltage difference, but it's no voltage applied, just the phase, everything is stationary. No energy is supplied. Still there's a current going between superconductors. One has to understand it's important that this current is periodic in this phase difference. Why is it so? Because each superconductor is completely characterized with a phase factor like this. Wrote for the two. So if you add 2 pi to any phase to this phase, it will just the same. It will be precisely the same superconducting state, right? So the current has to be the same. So the current is periodic in phase difference. That's one Josephson effect, DC Josephson effect. But okay, it was a logical step for him to reveal the relation between this phase and the fundamental electricity quantities, right? This phase comes about the broken gauge transformation, and this gauge transformation necessarily involves electrostatic and vector potential of magnetic field. We don't have to think about magnetic field in this chart. We have to think about electrostatic potential. And it turns out that the time the dependence of this phase is just voltage applied to a certain superconducting electrode. Now I'm talking about phase difference. So the voltage here is essentially voltage difference between two superconducting electrodes. Right. So if we apply voltage, the phase difference is not constant. It's running according to linear law. Very good. So let us substitute this running phase into this formula. And we get something rather strange. We apply constant voltage, but we get oscillating current. We get oscillating current because of periodic dependence of the current on the phase, and phase is just changes linearly. Right? The frequency of this current is solely determined by voltage applied, right? While the amplitude depends on the properties of the junction. Good. Two Josephson effect, single Josephson effect, in fact, but it has two facets: persistent current and the dependence of the phase on voltage. So we have, in fact, we have a relation between current and voltage in a little bit implicit manner. That can come as a surprise, although perhaps you have heard something about this Josephson effect. If you want to ask a question, yes, please. I would find it important at this stage, just to understand this unusual and peculiar physics involved, because further we will just exploit it. Should the superconductors be different, or can they be the same? superconductors can be different in the sense that they are different materials. That doesn't matter. Of course, there will be no current without phase difference. So whatever the superconductors, they could have different deltas, for instance, but they should have, there must be phase difference between these two superconductors, otherwise the current wouldn't go. Fine. All right, let me explain something important. No voltage applied. We are essentially in the ground state. We don't disturb the system anyhow. So the current appears to be a property of ground state of the structure. And using so, I would just derive the derivation is rather fundamental, but it's ultimately simple. I hope you find it useful. Under these conditions, I can derive the relation between current and energy which is accumulated at the junction. Okay, how? Let us see. I will change the phase in the superconductors very slowly. And I will look at the change of energy. Right. The change of energy first is the power dissipated. You know that power dissipated is current times voltage. So now substitute the current, which depends on phi, and voltage, which I have taken from the Josephson relation. Okay, I got the change of the energy if upon adiabatic change of the phase. From the other hand, I can look at this change differently. I know that energy depends on this phase. So if I take time derivative, what should happen? I have derivative of the energy with respect to phase times time derivative of the phase. Fine. Now I want to compare these two. And they have to be the same, and speed of the phase cancels, and I have this relation. So the current is just derivative of the energy with respect to phase, and in order to compute this current, I just need to know the energy of the nanostructure between two superconductors. I don't have to care about lots of energies which are accumulated in superconductors. Why is it so? Because energies of superconductors are degenerate with respect to phase. If I change the phase, nothing happens. So this energy, part of the energy which depends on the phase difference, is associated with the junction only. Fine. And let us quickly compute this energy. To this end, let us consider Josephson contact with a technique which we know in scattering approach. So how we can formulate this? So I take the same nanostructure I have used in normal superconductor stuff. One channel, same matrix, conjugated scattering matrix, conjugated matrix for complex conjugated matrix for holes. Which waves do I have? All right. I have incoming waves, electron waves to the nanostructure. They can be either electron waves or Hall waves, in principle. And outgoing waves, which can be either electron waves or Hall waves. So I have four waves because they can come from the left or from the right. And okay, that's all incoming waves, and nanostructure transfers them into outgoing waves. That happens separately for electrons and holes. Very good. That's what nanostructure does. What do the superconductors do? All right. In superconductors, there is Andreev reflection going on. So, for instance, this wave which went off the structure can return as an electron. This wave which went off the structure as an electron can return as a hole. That can happen separately on the left and on the right. So I have another relation. And what does it relate? It relates outgoing waves, waves that going from the nanostructure to the waves which come to the structure. All right. What does it mean? What does it amount to? If there is a wave in the structure, it should become the same wave upon applying both scattering matrices. Right? The wave should become the same. And there is a solution for this wave only if the product of these two reflections, normal reflection and wave reflection, has eigenvalue 1. That doesn't really happen for arbitrary metrics. Not all the matrices have the eigenvalue 1. But we have a parameter to tune which comes as Andreev phase into this expression. And that depends on energy. This means that this condition can be satisfied at certain energy. Fine. So we put all these vertices together. We find the energy at which this bound state can appear. That's what we got. It seems to be that at any finite phase difference between the structures, between the superconductors, sorry, there is a bound state, Andreev bound state, it is called, because it comes about Andreev reflection. It depends on, its energy depends on transmission coefficient of the nanostructure in a certain channel. For each channel, we have the state, Andreev bound state, and right, it lies entirely within the gap. So there's a gap, and all this factor is always smaller than 1. Good. What are the limits? Here I plotted this energy at different transmission coefficients. So small transmission coefficient gives me a state which is very close to the gap edge. Okay, it's periodic in phase as I promised. And if transmission coefficient is ideal, the energy of state just dives deep to zero and gets back. At intermediate transmission coefficients, it doesn't go to zero. Good. So there is Andreev bound state. In any nanostructure, funny enough, its energy doesn't depend much on superconductor, only on the gap in the superconductor, and it is determined by transmission in the nanostructure. Let's see, I need to accelerate a bit. Good. So if we have many channels, we have a bound state for each channel. Now I want to say something which looks very similar, but it's indeed it's a little bit different. We've been talking about positive energies, excitation energies. So one can create excitation in nanostructure with this particular energy. But by virtue of superconductivity, the energies of excitations also determine the energy of the ground state. And this is what we want to know. This is what we want to know. Eventually, we look at the phase-dependent part of the ground state energy. And to get it, I just need to sum up these positive energies and take it with minus sign. All right, that's what I do. So I get the phase-dependent part of the energy of the whole nanostructure. Now we are ready to evaluate the current. How we evaluate the current? Just differentiate it with respect to phase. Here it is. Again, it is small current if transmission coefficients are small. And in this case, okay, in this case, one can forget about this term. So the current is purely harmonic, first harmonics sine phi, and proportional to transmission coefficients. Otherwise, the shape of the current becomes more complex. And at t close to 1, it is, it's a sawtooth shape. The current goes like this, and it quickly drops just over here. So this is sawtooth. Fine. Sure, we have helped to Professor Josephson by deriving the concrete formula for this current in terms of nanostructures. Professor Josephson didn't know this formula, but by his time there were no much of nanostructures. We can specify two nanostructures which have been already known at the time. Of course, it would be just purely theoretical discovery, Josephson effect, which would be immediately forgotten if already by the time people could not master these contacts between two superconductors. And they did it in very simple way. The contacts have been large in 2 dimensions, but very thin in 1 dimension. This is something I have already explained to you. It's making a tunnel barrier between 2 metals. Right? Remember, one can take, for instance, aluminum, put a film of aluminum, and then let it to oxidize. So you might remember there's a thin layer of aluminum oxide, and put another aluminum. That's how they make contacts between superconductors 50 years ago. Right, tunnel barrier, small transmission coefficients. What we can do about this? Well, we could simplify the formula for the current. Then there's only a sum of transmission coefficients. So this is conductance, just conductance of the structure, in this case, conductance of the tunnel barrier, which defines some current scale, which is called critical current. You will see in several minutes why. Okay, I can say it's right away. It's a maximum persistent current which can flow through the junction. Critical current. Good. So it's proportional to the gap and it's proportional to the conductance. Fine, this is current. It's also important for us to get the energy associated with the junction. Here it is. This coefficient is called Josephson energy. The total energy is cosine of phase. Yeah, so if you take derivative, you get sine, you get current. And again, this Josephson energy can be expressed in terms of conductance of the junction. So the junctions with high conductance, they have higher Josephson energy. Fine. Now, in remaining 10 minutes, I will tell you something about Josephson junction in kind of realistic setup. And I will tell you about classical dynamics of a Josephson junction. So Josephson junction is a current versus something which is related to voltage. It's an element of electric circuit, rather peculiar element. Let's bring it together with other common elements of electric circuit. Right, we can consider one lead junction, another lead. What is about? There can be a capacitance between the leads, also related to the junction itself. It can be also some resistance between the leads, either through the tunnel junction itself or through environment between the junction, something which provides dissipation. So in this case, we have a certain model, capacitively shunted junction model for the Josephson junction. Good. The beauty of circuit theory is that you don't have to be a Professor Josephson or any other Nobel Prize winner to understand how does it work. You can derive the equations just as a piece of cake. How we do this? It's electric circuit, and the current, so the circuit is fixed. So we can use current conservation. Right, what currents do I have? I have Josephson current, which is this function of phase difference. I have a current through resistance. And don't forget that capacitors also can conduct current. This current is proportional to the time difference of voltage across the capacitor. Good, we're done. Now we just recall Josephson relation. So that becomes first derivative of the phase. And that becomes a second derivative of the phase. And just to make the stuff clearly, I have rewritten this equation in some frequency scale to make it kind of dimensionless. This frequency scale, it's called plasma frequency, and it is made from critical current and capacitance. And besides, I have quality factor, which tells me how much dissipation do I have in resulting system. So large quality factors means less dissipation. And this quality factor just proportional to the resistance. More resistance, yeah. Less resistance, high quality. Fine. Then what do I have to do? It's all equations. It's all equations. You look at the equation, you have no idea what is this. But it's just a matter of experience. You will understand everything in a second. First of all, this equation, which I wrote, it's very much like Newton equation for a particle which moves with inertia and friction in some potential. And this potential is called washboard potential. Perhaps some of you have ever seen a washboard. Yes, most plausible source are animated cartoons of last century. A washboard is a device to wash clothes, and it is a metallic plate which has a oscillating profile. Usually you tilt it and you apply your clothes and you wash it. Okay, that's not what we are going to do. We just notice that the potential we look at consists of oscillatory part and tilt, which is the current applied to the junction. Fine, sure, we have equation for a particle in this potential. Then we basically understand everything about Josephson dynamics using our intuition about particle motion. Let me first consider small tilts, which I can do in this picture. Yeah, here's a particle. What can it do? It can oscillate around the minimum of these potentials. These oscillations are of good quality if quality factor is small. If quality factor is big, these oscillations are quickly damped if quality factor is low. Anyway, if the tilt is small, the particle wants to sit near the minimum of the potential, right? What does it mean? It means that there is a finite Josephson phase at this junction, and there is a current going through. Let us increase the tilt, increase the current. If the current exceeds the critical current for the junction, this minima just disappear. This is at critical value, there are no minima. And what will happen to the particle? Of course, it will go down without any, nothing would stop it, right? The particle goes down. Now we call that the coordinate of the particle is the phase. It is a phase. And there will be finite time derivative of this phase. It means that there will be voltage across the junction. So if we exceed a critical current, we've got voltage state. We apply current, and the system will give us voltage as it is expected to be. Fine. Shall I sketch the curve? So if I plot current versus voltage now, there will be no current up to certain voltage. Then, okay, it depends. Let me consider large friction. Then it will increase like this. This will approach resistance which I have in my circuit. So the slope will be will correspond to Ohm's law at large voltages. So it's good, sir. I guess I'm done. And I'm even on time. Let me go quickly through all the slides. We have started with no, cannot go so fast as I expected. Anyway, we've been talking about quantum transport in superconducting devices. We discussed basic properties of superconductors. We understood the spectrum, it has gap, and that gave already us an idea of Andreev reflection, strange process where electrons are converted into holes. We understood it that also the same holds for the waves. Electron waves are converted to Hall waves. That gave us the basis of scattering theory. We applied to NS contact nanostructure between normal metal and superconductor. And we could kind of, with our fingers, we could compute something. We have computed Andreev conductance. Then we turn to contact between two superconductors. We understand Josephson effect, persistent current. We understand that the phase is set into motion if you apply voltage. Right, again, applying the same scattering theory, we could compute this Josephson junction. And in the end, we looked at this Washburn potential. We understood intuitively the classical dynamics of Josephson junction. That's it. That's what we did today. Thank you for your attention. I would like to stop the recording.